everybody. I'm going to be talking today about the new version of GVERSE Attributes 2016.1, things that we have added to it. But just in case you're not familiar with what GVERSE Attributes is, and just to refresh everybody's memory, basically GVERSE Attributes is our new tool for computing seismic attributes. Now there are many tools that let you compute seismic attributes, but we've basically rethought the whole approach, the whole workflow around how seismic attributes are computed and used in your daily interpretation tasks. So most attribute softwares that are out there, you can compute attributes, but you have to compute entire volumes of attributes. And by nature, seismic attributes are a very iterative sort of a process. When you're analyzing seismic attributes, you have to compute many different attributes, you have to try them, change parameters. And the traditional softwares, because you have to compute that entire volume, they take a lot of time. You spend a lot of time managing disk space, saving those volumes. Then you have to load those volumes into your interpretation softwares, and then open various inlines, crosslines, see if your attributes are actually adding value to your interpretation, if they're working for you, for your data in your area. If they're not, you have to go back, create more volumes, and so on and so forth. So with GVERSE Attributes, we've introduced on-the-fly attribute computation, so you don't have to compute an entire volume. What we do is you take an inline and you apply an attribute on it, and it's computed on the fly, and it's we have integrated viewers within the application which lets you see the results immediately. So you can navigate through your volume with an attribute applied to it. Any attribute can be a simple trace-based attribute to very computationally intensive curvature or geometric attributes like semblance, and you can go through your entire volume, choose the compare different attributes. We still have our multi-panel viewer where we can put attributes side by side. That's the panel we introduced in 2015.1. So you can look at many different attributes and then compare the ones that you want, choose your parameters, and then finally generate volumes only for the attributes that you actually need, that you know add value to your interpretation. In 2016.1, we have made a bunch of different enhancements, some very major ones, like we've introduced a 3D view, so you can visualize your attributes in a 3D space. You can look at your structures with actual attributes applied on your seismic, and you can see how they're spatially distributed in a 3D space. We've also added many specialized tools for an in-depth attribute analysis, and I'm going to take you through some of them as we go on through the presentation. Right, so before I go into the features that I'm going to show you, there's some behind-the-scenes stuff that we've also done. The first one was a big concern for our customers who use SegWi data. Because SegWi format is designed for storage, and it's not really a reading format, our on-the-fly attributes tend to be slower when you're using SegWi data. So we've added SegWi compression to it, which is basically a visually lossless compression. So we take a 4-byte SegWi and we encode it into a single byte. So you can now work with much larger SegWis. You can basically 4 times the size of the SegWi, approximately 4 times the size of the SegWi data. So you can work with much larger SegWi, and our computations are now much faster because we're now dealing with a lot less data. But the effects of the compression, the distortions by the compression are minimal, almost unnoticeable, and that's why we call it visually lossless compression. So you can now work with larger data sets, get quicker results, even when you're using SegWi compression. Then we've also introduced cache for our CAPS algorithms. CAPS is our continuous amplitude phase spectrum algorithm that we use for our spectral decomposition. And now what we do is if you do a CAPS with a certain set of parameters, we sort of cache that into our memory so that when you're computing attributes based on those spectrally decomposed data, you don't have to create that again and again. And again, this results to quicker results for all of our high resolution attributes, which are again very computationally intensive. Finally, we have the LOD format. We've introduced support for level of detail files. Now this is basically for visualization of very large data sets. So like if you have 50, 60, 70 gigabytes of data, what we do is we create LOD files, which is basically we create different levels of resolution in your data. And so we load the lowest resolution first so that you can start to see the trends in your data, and then go back and fetch other data and stuff it in the holes so that you can finally, as time goes on, your full resolution data is loaded. So this is especially useful when you're rendering volumes, because the volume, when you're looking at a volume in 3D space, you load all of that data. That's a lot of data that you have to handle. So this LOD format really increases your performance when you're loading volumes, or when you're navigating through a very, very big data set. So these are some of the behind-the-scenes improvements that we have done for our performance of our GVERSE Attribute software that helps makes it even faster. We've also reworked our user interface. In 2015.1, we just had one giant ribbon control, and all of the controls were actually within that ribbon. We've rethought that, and we have now reorganized our ribbon. We've added a sidebar as well. So a lot of the basic functions that you have related to the view are now available to you in the sidebar for quicker access. That also removes the clutter in our ribbon and helps us keep it more organized. We have context menus as well, context-based ribbons as well. So if you selected a certain 3D object, you're going to see options for that in the ribbon. But so you have options when you need them, otherwise they're not taking up space, and everything is very easy to find. All of our workflows are still centered around this attributes tree, which is basically the heart of our application. All of our attributes, which you can select, click and basically click and apply your attributes directly to your viewer. So, and we've tried to keep our workflows as simple as possible. Our aim is that people should be able to open this application and start to use it without any help by reading manuals or trainings. But our workflows are also, we try to keep the learning curve as small as possible, so that if you do need to refer to a manual, you have to do it just once. They're simple enough that once you go through the manual, see how it's done, it's going to be very easy to repeat that task. So basically, we've rethought and made our interface more interactive, much more simpler. Then this is the big feature that we have, the attribute analysis in 3D. So we've added a 3D space, a 3D viewer to the application, which helps you visualize all of your attributes in 3D, and you can obviously compute your attributes in 3D as well, on the fly attributes in 3D as well. And we've also introduced voxel rendering, so you can you can load entire volumes and then visualize a volume of seismic data with different attributes applied to it as well. And I'm going to give you a quick demonstration of what we can do with our 3D viewer. So just open my attributes application, and this is my basically default 3D viewer. It comes up with this grid for your survey. From the ribbon, you can add a bunch of different seismic objects in there. So let's say I want to open an inline. I can add cross lines as well, and a time slice. And all of my seismic data is now available in my 3D scene. I can select any inline, crossline, or time slice, or any object that I've added to my 3D scene, and apply attributes to it directly from this tree. And for example, if I apply instantaneous amplitude to my inline, it's applied. This is on the fly. Now, we don't have any data stored anywhere on this. This attribute was computed on the fly, and the results are shown to you directly. So I can apply a different attribute to each of these objects. So for example, I'm going to apply phase, instantaneous phase to my cross line, and let's say instantaneous frequency to my time slice. And these are again computed and displayed immediately in the 3D viewer. I can use my mouse to navigate my objects to different locations. So for example, I've taken my inline and I moved it to another location. And you can see this anomaly over here. This is instantaneous amplitude applied to my inline, and you can see this very bright spot right over here. And now this is the big advantage of viewing these things in 3D. Now I can take my cross line, I can move it right in the center of my bright spot, and let's say I apply instantaneous amplitude to it as well. and now I can see the inline and the crossline extent of my bright spot. If this was a 2D viewer, or if I was just working with 2D data, this would take me much longer than this, because I'll have to step through all of my inlines to see where my bright spot, my inline range for the bright spot, and then through my crosslines to see my crossline range for the bright spot. And similarly for the time slices for the thickness of the bright spot. And I can also move my time slice up here and apply instantaneous amplitude to that as well. And now I can also see the complete lateral extent of the bright spot. I can also add other inlines. So for example, I'm going to add another inline right over here, very close to the previous one I have, and I'm going to apply frequency attribute to it, and now I can see under the bright spot I have this sort of a low frequency anomaly. The red's giving me low frequencies. So again, I can quickly confirm if this bright spot is actually because of hydrocarbons or is it some geological effect. So that's how quickly you can now look at attributes and see the actual extent of your structures in 3D. Because of the 3D viewer, of course, and the on-the-fly attribute computation that we provide. We can also, all of our objects come up in this tree over here, the 3D objects tree. You can toggle displays on and off, or you can remove the entire line completely from the scene using this tree. The next thing I have, just let me move this out of the way. Right. So we can also add arb lines to our 3D scene. We've also added support for well data, so now you can see your well symbols. So if you have, right now we don't have support for well bores, but you can look at your well symbols where they are on your in your survey area, and then you can create arb lines. Let's say I create a well-to-well arb line, and this arb I can apply on-the-fly attributes to this arb line as well. So let's say I was looking at sweetness, how it goes from my, how it varies between my wells. So I can apply that attribute directly to my arb line, and now I can see how my sweetness attribute changes as I move from well to well. Finally, we can also add probes. Now probes are basically cubes of seismic data. So I'm just going to add a probe here. I can graphically resize it to whatever area I want to see. And it's going to add that probe for me. I can of course apply attributes to this probe as well. Let's try something more interesting like semblance. So I'm going to apply semblance to it, and it's going to compute it for all of these faces one by one, and it's going to now I have like a cube of seismic data, and I can see any attribute on it. Again, it's computed on the fly and shown to you directly in the 3D viewer. I can cut into my cube, and I can look at different faces as well. So like the chair cut mode, I'm just going to cut through the first inline that I have, and now I can resize my probe, and now you can see this discontinuity. You can see how it's going through my cube. So I could see it on the surface, but now with the chair cut mode I can actually see exactly how deep it goes, what it's doing down there, and then back up here again. So again, because of the 3D viewer, you can now, it's much easier to visualize how your structures are changing, how your features change, or how your attributes are highlighting your features, and you can see that directly in the 3D view. Now, a probe is basically just a six-sided cube, right? So you don't have data inside of this cube. Inside, it's basically empty. So if I zoom into inside the cube, you can see now that the inside of this cube is empty. You just have like data on the six faces of the cube. But we now have support for voxel rendering as well. So we can fill this cube up with data, with real seismic data. So For that, I just have to use this render volume button, and if I click that, now it's going to read all of that data inside the cube, and it's going to fill this cube up. Now, of course, I can't see through these faces, so I don't know what's inside of it. And if you look at the color palette control that we have, which we have also significantly changed. In 2015.1, this was basically just a drop-down which you could choose different color palettes. But now we've added the histogram support as well, so you can see the distribution of your data, what colors are assigned to which. You can see the color assignments, and you can play with the range and the transparency. So I can make the blues transparent. Let me go back here. So I can make the blues transparent, and now I can just see my high negative amplitudes. Right? So I have made everything else transparent, and now you can see, because this is a volume of data. So if this was just a probe, this is what you would see. You would see data on the surface only, right? But now, because I've filled this up with seismic data from the disk, I've filled this probe up with seismic data, now I can see inside the volume as well, because I've made my colors transparent. I played with the transparency, so now I don't see any of the blues or the whites, and I can see only the reds, and I can see how my surfaces are moving along. So that's basically voxel rendering. So we're rendering voxels, and we're showing you a volume of seismic data. But this, because volumes have a lot of seismic data, it's hard to do on-the-fly attribute computation on them. So you can't, because it's going to take, this is basically like generating a volume, right? So it's going to take a long time. So what we've done is we've added support for pre-computed attributes. So you can compute an attribute volume, and then you can load that attribute volume into the workspace, and then it starts to work just like any other on-the-fly attribute. So if I, let's say I have an attribute called average energy that I've computed already. So now I've computed this attribute for the entire volume, and I load that into my pre-computed attribute. So now this is now available as any other attribute. So if I had an inline, let's say I open an inline, let's look at our bright spot again. Let me hide this probe for a second. So this is our bright spot. If you go back to your instantaneous amplitude, you can see this bright spot again. Now if I were to apply average energy on it, this is what it looks like. This is what that bright spot looks like with the average energy attribute applied. And now I've created a volume for average energy. So to create a volume, I just have to go to my home menu, create a volume, choose the attribute that I want to generate a volume for. Let's say average energy. What's average energy? There it is. And then I add it to the current workspace, and I generate it. It's going to generate that volume, and it's going to add that automatically to my pre-computed attribute. But since I have that generated already, I just added that using the add button here. And now it's available here. So if I were to switch to this attribute, you're going to see basically no difference, because it's the same thing. It's the volume computed, and now you're going to see the same thing. But the advantage we have is when we're working with volumes. So now I can load that pre-computed attribute, and I can fill up this probe with data from this attribute. And then when I play with the transparencies, let me switch to a better color palette. Now when I play with the transparencies, so I can make all of the low average energy areas transparent, and just tweak it a little bit, and now I can see these bodies, these areas of high average energy, and they are isolated and they stand out really nice. So that's basically what you can do with voxel rendering. That you can, once you play with the transparencies, you can isolate your structures, and you can see, visualize exactly what your structures, your features look like with different attributes applied to them. Right, so that's basic. Also, you can add horizons and do a lot of other cool stuff in 3D as well. And I have a workspace open, and you can see this is basically the same probe that I had added earlier. If I just make this a little more transparent, you can see those bodies again. But also, if you look down here, I have a horizon added. This is the H-curve smooth horizon, and I have semblance applied to it. So you can see these faults. You can see them, how nicely they light up in semblance. And on the background, I have a probe with a cut applied to it, and I have the enhanced semblance attribute applied to that, and you can see how you can basically visualize exactly how well you've picked your faults in your horizon, basically, and you can compare them and see how well it works. So that's some of the stuff that you can visualize in 3D. This is another horizon that I have, which is called the MS4 smooth horizon, and you can see this channel feature in there. The attribute applied on it is basically a blend of 3 different attributes, and we're going to talk about that a little bit later. But right now I just wanted to show you the capability of the 3D viewer, and you can see how the different colors here show us the different frequencies and the frequency content, and like I said, I'm going to talk about that a little bit later. But you can visualize all of this very easily and in 3D. Another thing that you can do here is that if you have a bunch of different, so let's go back to my bright spot example. So if I have my inline here and I have my cross line here, again attribute applied to it, I have a time slice going through my bright spot. I can also view all of these in 2D, so I can go view all in 2D, and all of these now will be open in my multi-panel viewer side by side, so that I can actually compare and see what they look like. So, and I have cursor tracking as well, so you can see as I move my cursor in one window, I can see exactly where on the other windows I am, and you can navigate these individually to see what the attribute looks like in different parts of your data. So that's how we've also sort of integrated the 3D and 2D viewers together, so that you can use the both of them together simultaneously to get your results faster, to find attributes that work for your data quicker, and basically visualize what your structures look like. Okay. So that's what we've been doing in 3D. Next, we have a couple of very nice attributes that we've created, new attributes that we've created to help directly with your interpretations. These are the structure-oriented filtering and the automatic fault extraction attributes. Again, I'm going to launch a workspace to show these 2 attributes to you. So here I have my input data, and you can see it in 2D view right now, and this is an inline 425 through the middle of my seismic volume. Here we have a structural highlighting category, which is the new category that we've added in 2016.1. And the 3 attributes in here, the first one is the structure-oriented filter. So if I click that, now this is going to filter this data. Again, this is done on the fly, so your smoothing is done on the fly as well. And I have a bunch of parameters here that I can play with to fine-tune or to get the desired effect. So I have like I can change my smoothing neighborhood. I can see what effect it has. I can change the Gaussian smoothing factor to see what it does, and then so I can play with these parameters to basically filter my data. And actually, a good way to see this would be to use the secondary attribute overlay. So I can draw a rectangle on any area of my seismic section, and now I can apply that attribute, the structure-oriented filter attribute, to inside this rectangle that I've drawn, and you can see the effect of your smoothing very easily if you resize this rectangle. You can see as I move the rectangle, you can see what effect your smoothing is having, right? And you can of course play with the parameters to make sure that you're not losing signal and you're just getting rid of your noise. And once you're happy with that, again, you go to your export section, and then you just create your structure-oriented filter volume. Now this volume you can use either directly in your interpretation to pick horizons on noise-free data, or compute. You can import it into a GVERSE Attributes workspace, and you can compute attributes on filtered data as well. The other new attribute is the fault attribute. Now you'll see the fault dip and the fault strike attributes. Now these basically are the same thing, just the value that the output is different. So if I use the fault dip attribute, what it's going to do is it's going to take that inline, it's going to run it through our algorithm to find all of the places where it thinks there are faults. So these are all of the locations. So rest of the data is all empty, so we have this white space, and the colors are basically only at places where the attribute thinks there are faults. And you can see the color palette over here as well. And these are just the dip values, the dip of the fault. And if you use the fault strike attribute, the colors will represent the strike of the fault. So right now, you can see all of these different faults. But again, these faults hanging in the air doesn't really help you a lot, right? So the best way to, again, analyze these faults would be to use the secondary attribute overlay. So I can create a rectangle again, and I can apply the fault dip attribute to inside this rectangle. And let me make the background basically filter data, because that's going to help me visualize my faults better. And now inside this rectangle, I have these faults. And as I move this rectangle around, I can see where all of these faults are. And then I can, obviously, because this is an algorithm, it's going to have some false positives, it's going to pick some, and it's going to miss some faults, but you can tweak these parameters here to get exactly, so this is all of these different parameters, and you can, the results are shown to you, are updated on the fly, like everything else, and you can see what set of parameters actually works best for you to pick all of your faults. And then once you have all of your faults, you can again export a fault volume, and this volume will basically write data only at points where you have faults. And I have, you can also obviously see this in 3D as well, and I have this volume here, which is a pre-computed volume. So I generated a fault volume, and I added that to my workspace, and now I can visualize basically all of my fault surfaces. You can see where the algorithm found all the faults. And to get a better perspective on this, I have another probe here which with semblance applied to it, and I've cut into an inline, into a cross line of this probe. And now you can see basically how this in the last three cases here, and now you can see basically how your faults So basically, I've created a volume, and then I've superimposed that on my probe, and I can now see the fault surfaces and how they are actually, what they look like in 3D. So that's our automatic fault extraction attribute, which is a new one that we've added. Then we also have options to view multiple attributes simultaneously. These are blending options that we have, co-blending and RGBA blending. With RGBA blending, you can take 4 different attributes and combine them together to get one result. This is what I had applied to the horizon that I showed you earlier, and I have an example of this over here right now. So right now I'm looking at a time slice 1040, and on panel number 2 I have spectrally decomposed amplitude volume of 28 Hertz. On panel number 3, a spectrally decomposed amplitude volume of 40 Hertz, and on panel 4, 64 Hertz. And if I zoom in, you can see that there are this is a channel system here, which shows up in 28 Hertz, but if you look at the 40 Hertz volume, you have 2 channels, which this particular channel didn't show up in the 28 Hertz volume at all. And similarly, in the 64 Hertz, you don't see the stop channel, and you just see different features of a better tuned lower channel only. Now so this is all information that I have. I can now use RGBA blending So I can turn on my RGBA blending. I can take my red channel, I'm going to assign it 24 hertz amplitude. I'm going to take my green channel and I'm going to assign it 40 hertz amplitude. I'm going to turn this on, so now it's going to be part of the blend. So now what I have here right now is the same time slice, but I'm now looking at the 28 hertz and the 40 hertz together. So the reds are my 28 hertz and the greens are my 40 hertz, and obviously as the colors mix, I can see what part of the channel, what frequency is contributing more to what part of my image. Similarly, I can add the blue channel and I can give that, let's say 64 hertz, turn this on. Now it's going to add the 64 hertz component in there as well. So now I can see all of these, I can see these features much more clearly, and I can see, basically the three images that I have here, three separate images. I've combined information from all of these three into a single image. And this is what I had applied to that horizon earlier as well. So that's basically RGBA blending that lets you visualize multiple attributes simultaneously on the same section. We also have co-blending, which is basically an overlay of two different attributes. So, for example, I have this time slice here. I'm looking at some of these faults that are going through. So I can turn on my co-blending. Now, as the base attribute, I have my input data, and on the overlay, I can give it something that will help me identify my faults easier. Let's say semblance, and that is my semblance is now overlaid. So if I turn my overlay percentage to 0, I just see my input data. If I go to 100%, I just see my semblance. But if I put it somewhere in the middle, let's say around 50, 55, 60%, now I can see both of them together simultaneously. So I can see my semblance data and how my amplitude data relates to that. So you can do this for any two attributes, basically. And you can also play with the transparencies to make your results stand out a little more. So I can use my color palette, and because I'm just interested in low semblance areas, I can make all of the high semblance areas, I can make them transparent. So now only my low semblance areas are highlighted, and I can take this overlay percentage, I can move this to 100% so that my semblance stands out. And because all of my high semblance areas are now transparent, I'm just going to see my input data through that high semblance areas. And now I can see how my semblance actually relates to my faults. How my semblance data relates to my faults. And this actually works really well when you're looking at the automatic fault attributes, the fault dip and the fault strike attributes. So for example, I have these some profiles pre-saved. I call the fault overlay. You can create any combination, and you can save that using these buttons here. So these are all customized. So I have my fault overlay profile as the base attribute. I have my input data in grayscale. As the overlay, I have my fault dip in a flat red color palette, so everything is red, and with this set of parameters. Right? So you can basically save parameters in here as well. And now you can see how well our fault algorithm, or how you can judge how well your parameters for your fault detection are working by navigating through this data. So I can navigate through my different time slices, and because now I'm looking at these two attributes simultaneously, you can basically compare and see how your results are, how well your fault attribute is working. So this is basically co-blending, where you're looking at two attributes at the same time. So all of these tools are really important when you're doing attribute analysis, and we've sort of tried to provide them all together in one application. So we have a lot of small enhancements as well, like the redesigned color palette control. I talked about that earlier as well. So you have control for transparencies, sliders for controlling your range, histogram incorporated in there to see how your data is distributed. You can also edit your color palettes, create your own customized color palettes as well. Then we've also worked on the resolution of our 2D viewer in 2015.1. If you zoomed in very close, This is the image you would see, sort of pixelation of your data. But in 16.1, we've basically we now get a much cleaner image on very high zoom levels as well, like you can see over here. And then we have a bunch of different tools for quicker analysis, which includes the external attributes or pre-computed attribute support, which helps you render volumes. You can create an attribute volume in some other software, import that into the workspace to compare what your results look like. And obviously it helps with faster analysis because you have attribute already computed. You don't have to do it on the fly. So that second or two it takes to compute that attribute, you don't have to waste that either. And then we have other enhancements as well, like ability to choose an area to zoom into, resizing the secondary attribute, which I showed you as well, changing the orientation of your time slices, and support for well symbols. These are the requirements that you have. So because we all our on-the-fly attributes are done using the GPU, you need a very good graphics card. The minimum you must have is an NVIDIA GeForce 430 with a 1 GB dedicated VRAM. But we recommend a higher-end card, which is basically an X70 or an X95, with a minimum of 2 GB dedicated RAM. So yeah, and it works both on Windows 7 and Windows 10. That's not listed here, but we do support Windows 10 as well. So these are some of the best practices that we recommend our users follow when they're using GVERSE attributes. Number one is use brick formatted seismic. So that's basically the 3DX version if you're a SeisVision customer, because we do work with SegWi. We have really optimized our SegWi performance, but brick formatted seismic still works better. But if you are using a SegWi, we recommend that you read it into memory so that you get the same performance as a brick formatted file, and that you enable compression so that you can work with larger data sets and that you have less volume of data to do all your computations on. If you're a very large data set, try to work in a subset. We can create subsets within the application, so you can create a subset in inline, crossline, and time domains, so laterally and temporally. And if you have other applications that are taking up GPU memory, we recommend that you close them because that's going to help you with the formats. Again, if you're using very large data sets, use the LOD format. You have to create the LOD format using the utility, but you have to do that just once, and then you can leverage the level of detail, the performance improvements from the level of detail format. And if you have some attributes that you use very frequently, you can always add them as pre-computed attributes, and that will help you with a faster analysis as well.